Okay, so the next thing we do with the sample is that we measure something and then we predict what will happen in the future. And that prediction is based upon the model that we determined from a random sample, right? And therefore the prediction is random. And therefore it has a confidence interval, it has standard deviation, variance, everything else that we require for a random number. And so if now we will use the hat for prediction, so yp hat means that the predicted value when x is xp. And this is, I mean, you have examples in computer science and you have lots of examples in the financial world when they predict what will be the growth of the country, what will be the stock market value, or what will be, GNP and GDP and so on and so forth, right? All of those are predictions in the future. So they will put some value of x, use some past results to predict the future. And same thing we do in the models. We have a parameter that we want to change, and we say, well, if we change this parameter, the performance will become better or worse, or will be so much, right? So it's the same thing. So y hat is function of x. This is a random number, and therefore it depends upon what you are predicting. So this is important to understand. You could say that, well, if we take 100 samples in the future, then I am predicting the mean. Then you would be much more right, because now you are going to take the mean of 100 future samples. Then if you just say I will take only one sample in the future, and then you could be very far off, because that sample could be very far off from the mean, right? So you have to understand what you are predicting. So basically, if you are predicting the mean of m observations, then the formula is for standard deviation. The formula is standard of error, deviation of error, 1 upon m plus 1 upon n. M is the future observations, n is the current sample size, and then basically the prediction related to xp. Okay? If you are just going to predict one observation, then this formula becomes 1 upon 1, which is 1. If you are going to predict infinite observations, then this will become 0, 1 upon m, right? So it depends upon what you are predicting. So if you are predicting one observation, if you take a random sample and then you expect it to be, then you will need this kind of variance or standard deviation. M is equal to infinity, that is mean of a large number of observations, that 1 upon m goes away. And then once you know the standard deviation, you can use the confidence interval as usual. Only thing you need is the degrees of freedom. And this prediction has the degrees of freedom n minus 2. Why? Because we have used 2 degrees of freedom here. The x bar and SE both came from the sample, right? And in fact, that is what we had discussed when we talked about what is the errors degrees of freedom. Errors degrees of freedom n minus 2, and the same will apply to everything that is used in the prediction, because predictions basically you have the same problem, same degrees of freedom. So once you know that this is n minus 2, then you will go, and then you will use t quantile, and every time I say t quantile, when does t become z? Anybody remembers? 30. Yeah. So if n minus 2 is 30, let's say n is 32, then n minus 2 is 30, then there is no need to look up the t table, because you can as well look in the z table. Now at 29, 28, it is very close. So I mean, I'm not saying that you really have to have a 32 observations or 31 or 29, but the curve becomes very close to z near there. Okay. Now we are making an additional assumption. Remember, when we use t distribution, we are making one more additional assumption for small samples, and that assumption is, if we have large sample, then we don't need to worry about something. Normality assumption. We don't have to assume that the observations are normally distributed. Okay, if you have large sample. If you have a small sample, the only way you can analyze a small sample is if you assume normal distribution. Then t distribution comes in. Then t distribution saves you, basically, because we know what is the sum of squares of normals or sum of normals, but we don't know what is sum of exponentials if it is not a large number of exponentials. I mean, we probably know, but that requires a statistician to figure out what is the sum of two exponential, 3 exponential. We will talk about that actually. But if it is large number of any distribution, then it becomes normal, and therefore that's why we have to worry about this t. We will talk about t all the time, but basically it will become z if it is a large number of observations. Alright, now if you were to plot that confidence interval that we talked about, then you will notice this kind of phenomena. This shaded area is the measured range. So you measure the phenomena from here to here, and you are trying to predict either too far in here or too far over there. As you go farther away, your confidence interval goes wider and wider and wider. So if you do the measurement of the last 5 years and predict 50 years from now, you're not going to be very confident. On the other hand, if you predict next year, maybe very confident. So that's the phenomena here, is that you don't want to predict too far out, and that's what people do when they make, anytime I see something, well, in 2020, this country will be ahead of that country, who knows? Right? 2020 is not that far away, 7 years, but, people talk about, this will happen to this country or that country. I don't want to name the countries, but these things are very far off predictions, okay? And the confidence intervals are never stated, particularly in the news world or financial world, okay? And therefore, those values are just not believable. So that's the thing, is the goodness of the prediction changes, so confidence interval changes as you go off. So let's take an example. Using the disk I/O and CPU time data of example 14.1, so we have been working on this forever on this. Basically, this is CPU time formula, and we want to predict what will happen if the number of disk I/O is 100. Well, number of disk I/O is 100. The CPU time will be 24 seconds. And if you did the calculation of the standard errors, which we did before, that number came out. So now we are going to forecast, or we are going to calculate the confidence interval of the forecast. So we are assuming infinite observations in the future, and therefore 1 upon infinity, that term is gone, and we just put the rest of it. We get the standard deviation. We look for t value at 5 degrees of freedom. Why? Because there were 7 observations, so 5 degrees of freedom, and we are talking about 90 percentile, both sided, two-sided. So it is 0.95 quantile, and that gives us basically these values. So the prediction, which was 24.36, could be anywhere from 21 to 26 with 90% confidence interval. Now, if you were predicting just one observation, single observation, then you have to put 1 upon m, which in this case was 1 upon 1, and your confidence interval goes from 21 to 27. Let's see, it was 21.9, so almost 22 to 27, and now it is 21, which is 1 less, and it is 27.6 on the other side. So it has gone up a little bit. So actually it is not going up very much, which is good news, because the standard deviation of errors is so low, which may not always be the case. The standard deviation of error is just 1 compared to the observation, which is 24. So this is a really good model, and so the errors are very low, and that's why you are not seeing that kind of change. Then I'm going to change the topic now, and this is again very important, because this is somewhat distinguishes what we are talking about here from other places, is that we made several assumptions, and we need to verify that all those assumptions are valid, because a lot of time people just plot regression without verifying the assumptions, and then they come up with conclusions which are wrong. So first thing we assumed here was that the relationship is linear. That's why we are fitting a straight line, right? If the relationship is not linear, then you will have a line, you might even have an R square value, but it will not be realistic. Second assumption we made is that the predictor variable is not a random number either. It's just the, okay, everyone remembers what is predictor? Predictor is the X value. It's not a random number, it's the Y value which is the random number. And so that is second. Third thing is that the errors are statistically independent. And that's a difficult one to verify, but we will show you how. And that the errors are normally distributed with zero mean and constant standard deviation. So we assume, regardless of what the original observation is doing, we are not talking about the original observations, we are talking about the errors. Regardless of what the original observations we had, the errors are coming from a lot of observations combined together, so they become normal. Just like the mean becomes normal, the errors become normal. Okay? So we are assuming that they are normal, and not only that, they are coming with zero mean. Because if the errors are non-zero mean, that means that your whole thing is biased. That, you could easily fix the model for a zero error. Right? So that's another one. So we are assuming 4 things. And we have to verify all 4 things. And there are methods of verifying these, but I would prefer methods that are very easy and much more informative than the normal statistical tests. So first thing is to verify nonlinearity. And all of these methods, all these verifications that I'm going to talk about are visual. So you can see them right there. So first thing you want to verify is linear relationship. So one thing you should do is before when you do linear prediction or linear regression is to just plot y versus x and see if it is linear. Alright, so here are possibilities. This looks like a linear thing, so let's go ahead. This doesn't look like a linear thing, this looks like 2 lines, so you should not be trying to fit 1 line there. Maybe you should fit 2 lines there. This looks like a line except for this point. So maybe we should go back and check that point out as to why is it different. And then try to fit a model that really takes care of that difference, that reason why it is different, before we try to fit one straight line which goes to all the points. And this is clearly nonlinear. Then you should not be doing the regression. This is where you come up with, the thing is, let me just take this example. So suppose you are trying to forecast here, and you are not taking care of this problem. But how will you get the correct result? Because you really need to know what happens after this point. After this point, something happens in the system, and that causes the response to go up suddenly. No, so the thing is, this is what will happen again. Let's see. So you fit a straight line which goes here, but really the real system is going over there. This is where you will get the misguided conclusions. If you use the incorrect model, then basically you will get incorrect results. So first thing you need to do is to see whether it is anywhere close to linear. And this is where the art part is, because this may look like a linear or may not look like a linear, but I think this is very close to linear, right? And I will show you one more trick for finding whether it is close to linear. And then here again, same thing. If suppose you fit a line, this line clearly will be going like that, but the system is going here. And so you will not be getting the real correct results. By the way, this is called multilinear, as you can see, multiple lines. Okay. So that is one test. Second test is independence. Now independence, as I said, there is no foolproof test for independence. The only test is for correlation. So only thing we can prove something is dependent. We cannot prove something is independent. We just try to do a lot of dependence tests. If nothing is, we find, then we say, okay, it is independent. Alright? So with that thing, what we do is we predict we plot the error as a function of everything that we can. So here what we have done is we have plotted the error as a function of the response, predicted response, y hat. So we put for each observation, we have n observations. For each observation we calculate the predicted value of the response and we calculate the error in the prediction. right? It is not y, it is y hat. It is not x, it is y hat. So we predict the y hat and put the errors, and then we see the graph. Now when you look at this graph, this looks pretty random to me. Okay, when you look at this graph, this doesn't look pretty random to me. When you look at this graph, it doesn't look very pretty random to me. Right? So it's clearly what it says is these two graphs say that there is some relationship which has not been put into the model because the errors are related to the response. So there is a term which is missing still. I mean, in the worst case, you could fit a error regression to the error to the predicted response, and then somehow adjust the model to find what you are missing. But that is not, we will show you better methods. But anyway, so the thing is, you need to look at this and then you see if they look like random. Now, one thing is that one of the biggest tests you have to do first is that you have to look at the scale. So there is no scale on this right now, y-axis and x-axis. And so when we take the example which is coming right up, in the example, first thing you look at is the scale. If the scale is small, so let's say this was 0.0001, 10 raised to minus 3, and this was 1, 2, 3, 4, 5. Then we don't care. Who cares for 0.1% error? Whether it is linear or non-linear or whatever it is, right? So in practical world, while we are looking at all this, the first thing we look at is scale. If the errors are really small, then the trend doesn't count. Then you plot errors as a function of experiment number 0, 1, 2, 3, 4, 5, 6. Just the order. You're just trying to figure out whether the errors are independent, right? If they are still random, no problem. If there is a trend, then you know that there is something going on with the experiment. Maybe the cache is getting filled. Maybe the disk is getting filled. Maybe something is happening, so the system state is changing so that with more experiments you have more error. Or with more experiment you have less error, whatever the trend is. Everybody gets this point? That this is second part of the same independent error assumption. We are trying to just verify dependence. And if we don't find dependence, we move on to the next dependence test. Third, normally distributed. And that one we have all worked out very well because we know how to test for normality, and that is the QQ plot. Right? So we do the quantile, normal quantile, and we do the residual quantile, which is the error quantile. And then if it comes out very close to a straight line, that means the normality assumption is valid. If it doesn't come out very close to the straight line, there is some kind of trend, then we have to worry about what to do for that. And there are ways of interpreting and fixing the model depending upon what this graph looks like. Fourth is the constant standard deviation of errors. So the standard deviation of errors is basically when you plotted this thing, the standard deviation actually shows up by actually what we are talking about is what we call the spread in the error. The spread shows up as the minimum or maximum, or or some kind of range or distribution or whatever you want to call it, right? So there is a spread you can see is kind of constant. If the spread is such that the errors have a wider variance at some value of response, then there is a problem, right? And so we need to fix that, and there are ways of fixing that which we'll talk about. So that is the fourth test. Okay, so what happens is people plot a bar chart you're talking about. In the bar chart they put the errors. So what you're saying is when we make a prediction, so there is a standard deviation of the prediction. I'm talking about the standard deviation of errors. Okay, so I just want to make sure, because the standard deviation prediction could depend upon x value, but the error should not depend upon x value, right? So what I was going to check was this formula. The standard deviation of prediction does depend upon xp, and so if you see that the predictions are becoming more and more, but that is normal, the spread goes more and more for the predictions, but that should not apply to the errors. So that's why you should really do a separate test just for the errors. Now, so let's take an example. So the same, our favorite example of disk IO and CPU time. We did do the first, this is a linearity test, looks like linear to us. Then we did the errors as a function of response time, predicted response. And now here is the art part. Some people will feel that maybe this is going down or something like that, the spread. Or some people will feel it's the same. For a small set like that, it's difficult. But what saves us here is the scale. So the scale here is in the tens, goes up to 30. The scale here is in ones, goes up to 1.6. All right. So the errors clearly are less than 10%, or maybe less than 5% of the response. Right? The ratio is 1.6 divided by 30 or 30 divided by 1.6 is more like 20. Right? So the errors are less than 5% of the response. Is this good enough? If this is good enough, then we don't care what the trend is and things like that, because in the real world 5% error will make no difference. So our model is good, right? On the other hand, if this 5% is going to cause millions of dollars of damage, then we better look at as to why this thing is looking like what it's supposed to is looking, and we want to have a better model. So that is so that basically says that the errors do look random, for 5, because they are less than 5%, and then we are ignoring the trend. Second thing is normality. So now we look at the normality graph, and here they are pretty good. I mean, it's actually, it is pretty close to the straight line. And again, if these numbers were large, then I would be very careful about any of these. But if these numbers are small, I am going to forgive the deviation here, because all we can do is improve the model by 5%. Right? So I'm not going to spend a lot of my time, which is expensive time, on saving something which is very little cost. Right? So that's the real world situation, is that if this scale is small and it is acceptable, then other tests we can compromise. And that's the difference between an engineer and a scientist. I mean, an engineer is basically makes a workable system, and the scientists they just want the last digit, this and that, right? When they're mathematician. So the engineers are more real world practical people. Second example we did was the Unix versus Argus. So you see the residuals. The scale here is 80, and the scale there is 16. So what is the error range? I mean, compared to the response, 20%. 16 upon 80 is 20, right? I mean, 18 upon 60, whatever, I mean, 1/5. 20% error. Is this good enough? Maybe not. I mean, the thing is, this again, it depends upon the system. The people who are designing it, they can tell you, but I think it looks large to me, right? And then we look at this graph, we find the same thing. Is it linear? I mean, there is a significant deviation, and I'm concerned because the number is 16 here compared to this 80. If it was 1.6, then I would not worry about this. So the summary. So what we have done is we have shown basically, and we took the simplest model. Why did we go to regression linear model? Because this gives you all the things that you need for any complex model. And we will talk about a lot more complex models later on. But at least we learned few principles. We learned that everything that we estimate from a sample is a random number and therefore needs a confidence interval, which means whether it is a parameter of the model, whether it is a prediction, whether it is a mean, anything. Second thing we learned is that how basically all these formulas we learned basically, but we also learned that there are lots of assumptions we make in the model. So all of these assumptions that we talked about here, we will make in any other model that you make, any complex model. Right? And you need to verify each of those assumptions. And we learned how to visually verify, and how to practically verify those models. Because if you go to statistics books, they just talk about very strict tests and all that, which does not give you the information that you really need to make a practical decision in a short time. And so let's see. Terminology, we now know what is a simple linear regression model. What is simple about it? Yeah, simple is for single variable. Obviously, linear is for linear relationship, and you could have a non-linear relationship, and you could have more than one variable. Sum of squares. So now you know what are the sum of squares. SST, SSY, SS0, SS E. And then from those sum of squares, you can get mean squares by dividing degrees of freedom. And you know how the degrees of freedom come about. They add up, just as we explained. And therefore, now with sum of squares, we can talk about the variation. That's the new term we introduced. So all of these terms we are going to use in more complex models. Then we talk about coefficient of determination and correlation coefficient. So we saw how they are related. Coefficient of determination is R square. Right? That tells you what percentage of the variation is explained by the model. 90%, 95%, whatever, that R square. Correlation coefficient is that R actually, right, which is between 0 and 1. So if your coefficient of determination is 81, then the correlation coefficient is 0.9. Right? So you should distinguish between R and R square. All right, so now you have homework number 14C, and that basically adds to A and B, whatever you are doing, the visual test. All right, so that finishes this chapter. Now please do read the book, because there is a little bit more in the book, little bit more precise, more explanation. And so don't just do the homework because you have heard everything in the class.